Right now, somewhere in this galaxy, a star is collapsing under its own weight, and inside it a region is forming where the road simply runs out. Not into a wall, not into another place. Every path that reaches it stops, and there is nothing on the far side, because there is no far side. Our best theory of gravity says these places are being manufactured continuously out of ordinary stars by an entirely ordinary process, and that inside them, time itself comes to a genuine stop while out here the evening carries on. But there is a second argument, older than the physics by more than 2,000 years, which says that time stopping is not merely unpleasant, it may be impossible to even say. Both of those things appear to be true at once. So what happens when the most successful theory in science predicts something that cannot be described? By the end of tonight, you will know exactly what that paradox is. Settle in, subscribe if you have not already, and stay with us, because the ways out of this are not repairs, they are trades, and what each one costs is the part nobody mentions. Let's begin. Part 1. The End of All Endings. Nothing you have ever watched end has actually ended. I want to start there, because it sounds like a word game and it is not. Think about the last time you saw something finish. A fire burning down to nothing in a grate. A wave breaking on a beach and sliding back. A building coming down. A person you loved. Gone. In every single one of those cases something ended, and yet nothing was subtracted from the universe. Not one atom. Not one unit of energy. What ended was an arrangement. The stuff carried on. The fire is the cleanest example, because it looks so much like destruction. Wood goes into a grate and ash comes out, and it feels like a subtraction, like the wood has been used up and taken away. It has not. Almost all of the mass that was in that log left the room as carbon dioxide and water vapour, and it is now somewhere in the atmosphere, moving through the world, waiting to be pulled back into a leaf by a tree that has not sprouted yet. The log did not stop existing, it changed address. Our own bodies work the same way, and this is the version that matters most to people, so let us not be delicate about it. When we die, our bodies break down, and the material we're made of goes back into the soil and into the air. Bacteria take it apart, root systems take it up. Carbon that spent a few decades being somebody's hand ends up being part of a tree, or a beetle, or the wind. In a purely physical accounting, nothing is lost at all. Every atom in you tonight has existed for billions of years and will exist for billions more, and the arrangement it is currently participating in, the one that is listening to this, is one of countless arrangements it has been part of, and one of countless more it will join. Stars do it too, on a longer schedule, and at a scale that makes the point better than anything terrestrial can. A massive star burns for a few million years, exhausts its fuel, collapses, and throws most of its mass violently back out into the space between stars. That material does not sit there as debris. It becomes the raw ingredient of the next generation. It becomes new stars, and around those new stars it becomes planets, and on some very small number of those planets it becomes oceans, and eventually it becomes people who look up and wonder where they came from. The iron in your blood was in the core of a dying star. The oxygen you are breathing right now was manufactured inside something that exploded before the sun existed. Death, out there, is the supply chain. So the pattern is completely consistent. Everywhere we look, at every scale we can examine. There is no such thing as a final ending. There is only handover. The form ends and the substance continues. And because the substance continues, something always happens next. Which brings us to the assumption underneath all of it. The one nobody examines, because it never needs examining. Whatever happens, there is an afterwards. The afterwards might be unrecognizable. It might contain nothing that anybody would want to be part of. It might be cold and dark and empty, but it exists, and things go on occurring inside it, and the clock keeps running whether or not anyone is left to read it. Modern physics contains one specific circumstance in which that assumption fails. Not the ending of an arrangement, the ending of the afterwards itself. Physicists have a name for those circumstances. They call them singularities, and we are going to spend a lot of tonight on them, so I'm not going to explain them properly yet. What I want you to sit with for a moment is only the claim, stated as plainly as it can be stated, that a singularity, according to the theory that currently describes gravity better than any theory has ever described anything, Time does not slow down. It does not become empty. It does not become boring. It stops. There is no next moment, not an empty next moment. No next moment at all. And if that is true, if time itself can come to a genuine stop, then what we're talking about is the end of all endings. I want to be careful here, because that sounds like a phrase somebody reached for to sound impressive, and it is actually a technical statement. An ending is a transition. It is one state of affairs giving way to another. That is what the word means, and it is why every ending you have ever witnessed came with a handover attached. But a transition requires a later state to transition into. Take away the later state and the transition cannot happen, which means that at the end of time, nothing ends, in exactly the same way that nothing begins, and nothing continues, and nothing waits. There are no more endings because there is nothing left for an ending to be made of. That is a different kind of unpleasant from the apocalypses we're used to. Consider the ones people usually have in mind. An asteroid the size of a mountain hits the Earth, and it is a catastrophe of a scale that is genuinely difficult to hold in your head. And there is an afterwards. There is a very hot morning, and a long winter, and then a strange quiet world, and eventually something new crawls out of the ocean. The sun swells into a red giant and swallows the inner planets, and there is an afterwards to that too. A white dwarf cooling slowly, surrounded by whatever survives. Even the heat death of the universe, which is about as bleak as cosmology gets, has an afterwards. It is a very boring afterwards, but the clock is still ticking in it. Time is still passing. That is the thing all of those scenarios have in common, and it is the thing that makes them survivable as ideas, even when they are not survivable as events. A singularity does not offer that. There is no long quiet afterwards. There is no cooling. There is no waiting for something new. The road does not lead somewhere unpleasant. The road stops, and there is not even a wall at the end of it, because a wall would be a thing, and a thing has to be somewhere, and somewhere requires a when. Now here is what I find most interesting about this, and it is the reason it is worth 2 hours of your evening. This idea was not available to anybody before 1915, not to a physicist, not to a philosopher, not to a poet. For all of recorded history before that, the question of whether time could stop was not a hard question. It was not even a question. It was a confusion, in the way that asking what is north of the North Pole is a confusion. Something changed, and what changed was not our knowledge of endings or of black holes or of the universe. What changed was our understanding of what time actually is. For thousands of years we had the wrong picture, a picture so intuitive, so obviously correct, that almost nobody thought to check it. And when somebody finally did check it, the answer that came back did not just adjust the picture, it removed the flaw. Part 2. When Time Stopped Being a Metronome. Isaac Newton wrote the sentence that governed how everyone thought about this for 230 years, and he wrote it almost in passing, in a short explanatory note near the beginning of the Principia. Absolute, true and mathematical time, he said, flows equably, without relation to anything external. Read that again, because it is one of the most successful ideas in the history of thought, and it is also completely wrong. Time flows evenly. It does not depend on anything. It is not affected by what happens inside it. Somewhere behind the universe there is a clock, and that clock is running at 1 second per second. Everywhere. Always. And every event in creation is stamped against it. The universe keeps a beat, and the beat does not care what you do. If that is the picture you're working with, then asking whether time can end is not a hard question. It is a category error. You might as well ask whether the number line can run out or whether north can stop. Time, on Newton's picture, is not the sort of thing that can be damaged, because it is not the sort of thing that participates. It is the stage. Stages do not get injured by the play. Einstein took the stage away. What general relativity says, and I want to build this slowly, because everything else tonight rests on it, is that time is not behind the universe. It is in the universe. It is part of the thing being described, not the background against which the description happens, and because it is part of the thing, it can vary. It runs at different rates in different places. It responds to what is around it. The image I keep coming back to is that we thought the universe was following a metronome and it turned out to be a jam session. There is no single beat. There are many local rhythms, and they are all valid, and they drift against each other depending on where you're standing and how fast you're moving and what is nearby. Two clocks that agree perfectly when they sit side by side will disagree if you separate them and then bring them back together, and the disagreement is not an error in the clocks, it is a real difference in how much time each of them experienced. This is not a subtle theoretical claim. It is one of the most heavily verified facts in physics, and it is running in your pocket. The satellite navigation system in your phone works by timing radio signals from satellites about 20,000 kilometers up. Those satellites are further from the Earth's mass than you are, so their clocks run faster than yours, by about 38 microseconds per day. 38 microseconds sounds like nothing, 38 millionths of a second. But light travels 300,000 kilometers in a second, so 38 microseconds of error becomes about 11 kilometers of error on the ground, and it accumulates every single day. If the engineers who built that system had used Newton's picture of time instead of Einstein's, the whole thing would drift into uselessness within an hour of switch on and would be off by the width of a city by the end of the week. Every time a navigation app puts a blue dot on the correct street, it is a small experimental confirmation that time does not run at one rate. The effect was measured in a laboratory long before there were satellites. In 1959, two physicists at Harvard, Robert Pound and Glenn Rebka, set up an experiment in a tower 22.5 meters tall, about the height of a 7-story building. They fired gamma rays from the top to the bottom and measured, to a few parts in 1,000 million, that the radiation arriving at the floor was shifted exactly as much as Einstein had predicted it would be. Einstein made that prediction in 1907, 8 years before he had even finished the theory. It took half a century for anyone to build an experiment sensitive enough to check it, and when they did, it was right. In 1971, two more physicists, Joseph Haefel and Richard Keating, took 4 cesium atomic clocks and simply bought them airline tickets. They flew them around the world eastward, then westward, on ordinary commercial flights, and compared them against clocks that had stayed on the ground. The eastward clocks came back having lost roughly 59 nanoseconds relative to the ones that stayed home. That is not a large number. It is also exactly the number the theory said it would be, and it was obtained by putting scientific instruments in economy class. There is an even simpler demonstration falling through the roof of your house as you listen to this. When cosmic rays strike the upper atmosphere, about 15 kilometers up, they produce particles called muons. A muon is a heavier cousin of the electron, and it is desperately unstable. It survives on average about 2 millionths of a second before it decays. Even travelling at nearly the speed of light, 2 millionths of a second gets a muon roughly 600 meters. It should be mathematically impossible for any meaningful number of them to reach the ground, and yet detectors at sea level are struck by them constantly, thousands per square metre every minute. The reason is that from the muon's point of view, far less time passes during the trip than passes for us. The particle is not cheating. It is simply running on a different clock, and that clock is the reason it survives the journey. Every second of every day, the sky is raining evidence that time is local. Since then, the measurements have become almost absurdly precise. At a laboratory in Colorado, physicists have used optical lattice clocks, the most accurate timekeeping devices humans have ever constructed, to detect the difference in the flow of time across a height difference of about 1 millimeter. 1 millimeter. Raise a clock by the thickness of a credit card and it starts running faster, and we can now see it happen. The astronauts Scott and Mark Kelly are identical twins, and after Scott spent 340 days aboard the space station, the two brothers were separated by about 5 milliseconds of elapsed time, 2 lives that started at the same instant, no longer quite in step. Einstein himself found the implications hard to live with, and the most quoted thing he ever wrote about it came near the end of his life, in a letter to the family of his oldest friend, Michel Besso, who had died a few weeks before Einstein did. He wrote that for people like them, who believe in physics, the distinction between past, present and future is only a stubbornly persistent illusion. That line has been pulled in 100 directions since, and I am not going to lean on it too hard tonight. But the word worth noticing in it is stubbornly. He is not saying the illusion is silly. He's saying it will not let go of you, even when you know better, which is a strange thing for a man to write about his own field, and a fair warning about what the rest of this evening is going to feel like. Now here is where this stops being a curiosity and becomes the foundation of everything that follows. In general relativity, gravity is not a force that reaches out and pulls things. That was Newton's description, and it works beautifully as an approximation, but it is not what the theory says is happening. What the theory says is that mass and energy change the geometry of space and time around them, and that objects simply follow the straightest available path through that changed geometry. And one of the most important components of that change is that time runs at different rates, at different distances from the mass, which gives you a strange and rather beautiful way of describing what happens when you drop a stone. The stone is not being tugged. The stone is moving toward the region where time runs slower. Everything falls towards slower time. The pull you feel in your legs right now, holding you into your chair, is not a rope attached to the center of the earth. It is you, continuously failing to fall down a gradient in the rate at which time passes. The floor is the only thing stopping you. Sit with that for a second, because it inverts the usual hierarchy completely. We tend to imagine gravity as something that acts on things, and time as a separate matter, ticking away in the background while the acting happens. It is much closer to the truth to say that gravity is what time does when there is a lot of mass nearby. They are not two phenomena, they are one phenomenon, looked at from two angles. And once time is a participant, once it is something the universe can bend, stretch, slow, and reshape, then a new class of question opens up, and there is no way to close it again. If time can be slowed, how much can it be slowed? If it responds to mass, what happens when there is an extraordinary amount of mass in an extraordinarily small space? Is there a limit? And if there is a limit, what is on the other side of it? Einstein's own equations answered those questions. The answers were not reassuring, and it took the better part of 50 years before anybody was willing to believe them. Part 3. The places where the music stops. We need to be precise about what a singularity actually is, because almost every popular description of one is misleading, including most of the descriptions I grew up with. A singularity is not a place where the density is very high. High density is common. The center of a neutron star is so dense that a sugar cube of the material would weigh about as much as Mount Everest, and there is nothing singular about it. It is just very compressed matter behaving in ways we can calculate. A singularity is something else entirely. In general relativity, a singularity is defined by a property with the rather bloodless name of geodesic incompleteness. Here is what that means in ordinary language. In relativity, everything that moves through the universe traces a path through space and time. A world line. Your world line runs from the moment you were born to wherever you're sitting now and onward into your future. Light traces world lines. Planets trace world lines. And normally those paths can always be extended. You can always ask what happens next along the path, and the theory will tell you. A singularity is a place where you cannot. Follow certain paths in certain regions and they simply run out. Not into a barrier, not into another region, not into a boundary with something on the far side of it. They terminate, and when you ask the theory what happens after that, the theory does not give you a wrong answer or an infinite answer. It gives you no answer, because in its own terms there is no after to describe. For a long time nobody thought this was real. The singular solutions that people knew about all had something suspicious in common. They were perfectly symmetric. Carl Schwarzschild produced the first exact solution to Einstein's field equations in late 1915, remarkably, while serving with the German army on the Russian front. He sent it to Einstein, who was impressed and slightly startled that anyone had found an exact solution at all. Schwarzschild died a few months later of an autoimmune disease he contracted in the trenches. His solution contained both the horizon and the central singularity, and for the next 50 years almost everyone assumed that both were mathematical artifacts of the perfect spherical symmetry he had assumed. That assumption was reasonable. Real stars are not perfect spheres. Real collapse is messy. Real matter is lumpy and spinning and uneven, and the expectation was that a realistic collapsing star would miss the exact center, swirl around it, and bounce, the way real matter always does when you try to make it converge on a point. Nature abhors a coincidence, and a genuine singularity requires an infinite number of things to happen at once in exactly the same place. In 1965, Roger Penrose proved that expectation wrong in a paper 3 pages long. What Penrose introduced was the idea of a trapped surface. Picture a sphere of light expanding outward from a flash. In ordinary space, that sphere grows. Now compress enough mass into a small enough region, and something extraordinary happens to the geometry. The outward-going light rays stop getting further apart. Even the ones travelling directly away from the centre are converging. That closed surface from which nothing, not even outward-directed light, can spread out, is a trapped surface. And Penrose showed that once one of them forms, a singularity is unavoidable. Not likely. unavoidable. Regardless of symmetry, regardless of spin, regardless of the details of the matter, provided only that gravity behaves attractively in a very general sense. 5 years later, in 1970, Penrose and Stephen Hawking published a unified treatment that extended the same reasoning to the universe as a whole. On the same very general assumptions, our universe must contain a singularity in its past, not might, must. In 2020, Roger Penrose received a share of the Nobel Prize in Physics for this work, and the citation is worth quoting almost exactly because it names the thing precisely. He was honoured for the discovery that black hole formation is a robust prediction of the general theory of relativity. Robust. Not a curiosity, not an artifact, not something a more careful calculation would clean up. Something the theory forces on you whether you like it or not. Penrose and Hawking shared the Wolf Prize in Physics in 1988 for this work, and it is worth pausing on what a strange thing they had done. They had not observed anything. They had not built an instrument. They had taken a set of equations that everybody already accepted, applied a piece of geometry that nobody had thought to apply, and demonstrated that the theory contained a catastrophe nobody had put into it. That is a very particular kind of scientific event. It is the discovery that a house you have lived in comfortably for 50 years has a room in it you had never opened. So we should say plainly what that means for the subject of tonight. Within general relativity, the end of time is not an optional extra. It is compulsory. These are not places the universe might happen to contain. They are places it has to, and there are 3 of them worth knowing about. The first is behind us. The Big Bang, 13.8 billion years ago, is a past singularity in exactly this technical sense. This is where most popular accounts go wrong, so let me be careful. The Big Bang was not an explosion of matter into empty space. Run the expansion backwards, and what the equations describe as you approach that moment is not a very small hot ball sitting somewhere. It is the failure of the description itself. Every world line in the universe traced backwards terminates there. There is no earlier, not in the sense that the earlier part is unknown, but in the sense that the theory has no earlier to offer. The second is ahead of us, and it is the one that would take everything. If the expansion of the universe ever reversed, if the whole thing stopped growing and began to contract, then the endpoint of that contraction would be a future singularity. The big crunch, the Big Bang in reverse, everything falling back together, density climbing without limit, and at the end of it, time stopping, everywhere, at once. That scenario is not currently favoured, and I want to be honest about that. The expansion is not slowing down, it is speeding up, and has been for about 5 billion years. But it has never been formally excluded, and recent measurements have made the long-term behaviour of that acceleration a live question again rather than a settled one. The third kind is happening right now, and it is by far the strangest structurally. Inside a black hole, according to general relativity, time ends, but only in there. The rest of the universe carries on completely undisturbed. Your evening continues, the stars keep burning, and a few thousand light years away there is a region where world lines terminate, and nothing about that fact reaches out and touches anything else. I find that genuinely difficult to hold in my head, and I think it is worth being explicit about why. We tend to imagine the end of time as a universal event, the last tick of a universal clock. It does not have to be. It can be a regional matter. There are, on current estimates, tens of millions of stellar mass black holes in the Milky Way alone, formed the ordinary way, from ordinary stars that ran out of fuel. At the centre of our galaxy there is a supermassive one with about 4 million times the mass of the Sun, with a horizon roughly 12 million kilometres across, enough to swallow the orbit of Mercury. Every one of those objects is, on the classical description, a place where the road runs out. And there is one more feature of the geometry inside them that changes the whole picture, and that almost nobody mentions. Inside a black hole, in the standard solution, the roles of space and time swap. The radial direction, the direction we would ordinarily call inward, becomes time-like. The time direction becomes space-like, which means the singularity is not a location sitting somewhere ahead of you in space, waiting to be reached or dodged. It is a moment sitting ahead of you in time. There is a loose end here that has never been tied, and it deserves a sentence because it is the difference between an unsettling situation and a genuinely alarming one. In 1969, Penrose proposed what is called the cosmic censorship conjecture, the idea that nature always hides its singularities behind horizons, so that the places where physics breaks down are permanently fenced off from the rest of the universe. It is a very reasonable-sounding proposal. It is also, more than half a century later, unproven. Nobody has been able to demonstrate that the fence always holds. If it does not, if some collapse somewhere can produce a naked singularity, exposed to the outside, then the end of time is not safely sealed away in places nobody can reach. It is an ordinary part of the scenery, and if you want a number for how quickly it arrives once you're inside, the answer is unsettlingly domestic. For a stellar mass black hole, the time on your own wristwatch between crossing the horizon and reaching the singularity is measured in tens of microseconds. For a supermassive one, it stretches to tens of seconds, not billions of years, not an eternity of falling, under a minute on a watch that keeps working normally right up until there is no more time for it to keep. You cannot steer away from it for the same reason you cannot steer away from next Tuesday. Part 4. The Worst Death. Let me take you there, because there is no substitute for it. Imagine you are falling towards something very large. Not a stellar mass black hole. Those are small and violent, and they would take you apart long before you arrived anywhere interesting. Imagine something with 4 million times the mass of the Sun, like the one at the centre of our own galaxy. The horizon of an object like that is millions of kilometres across, and the geometry near it is gentle. Gentle enough that you can fall across it without anything happening to you at all. You are falling. There is no wind because there is no air. There is no sense of speed because there is nothing beside you to move past. Below you there is a darkness that is not a surface, and it does not get closer in the way that a surface gets closer. Around its edge the light of the whole universe is smeared into a thin, bright ring. The sky folded up and wrapped around a hole in itself. You cross the horizon. Nothing happens. That is the part people never believe. There is no shudder, no boundary, no alarm. Your watch keeps ticking at exactly 1 second per second, because your watch always ticks at 1 second per second. You look at your hands, and they are your hands. You look behind you, and the stars are still there. Nothing in your local surroundings has changed in any way that you could detect, and if nobody had told you where the line was, you would not know that you had crossed it. But something has changed, and it is not in front of you. It is in the structure of what the words in front of you now mean. Before, the centre was a place, somewhere below, somewhere you could in principle steer away from. Now, it is not a place. It is a time. It is a moment on your own personal calendar, and it is coming the way tomorrow comes. You have, by your own watch, something like 20 seconds, and what waits at the end of those 20 seconds is not an impact. It is the last moment, not the last moment of your life. People have last moments of their lives constantly, and the universe absorbs them without noticing. This is the last moment, full stop. There is nothing on the other side of it, and there is no other side of it. That distinction, between being destroyed and being ended, is the whole reason this subject is worth thinking about, so I want to unpack it carefully. Every death that has ever happened on Earth has been a reorganization. That is not a comforting thing people say at funerals, it is a physical description. When a person dies, the matter persists, the energy persists, the causal chain persists. A person's last breath is still, in a strictly physical sense, propagating through the atmosphere. The molecules that were in their lungs are now somewhere in the air of the world, and the tiny pressure wave of their last exhalation is still, in principle, out there, indistinguishably mixed into everything else but never actually deleted. The information is scrambled beyond any hope of reading, and it is not destroyed. The universe does not have a delete key, it only has a shredder. At a singularity, none of that holds. The world line is not redirected, it is not scrambled, it terminates. There is no recycling, because recycling is something that happens later, and there is no later. The atoms that were you do not go into the soil, or the air, or a tree, or the next generation of stars, because there is no soil, or air, or tree, or next generation on the far side of the last moment. For the first and only time in the entire physical description of the world, something is genuinely subtracted. It helps to compare it to the version of dying that most of us find bearable. When people say that the atoms in their body will go on to be part of something else, they are not being sentimental. They are being accurate, and the accuracy is the reason it consoles. There is a real continuity. The carbon that spent 70 years being somebody goes on to spend the next 4 billion years being other things, and some of those things will be alive, and some of those things will look up at the sky. It is a genuinely reasonable thing to take comfort from, and it is one of the very few pieces of comfort that survives contact with a physics textbook. What relativity describes at a singularity is the one circumstance in which that comfort is simply false. Not exaggerated, not oversimplified, false. And what makes it land, I think, is that it does not require you to believe anything at all about souls, or meaning, or purpose, or what happens to a person. It is a claim about bookkeeping. It says the ledger does not balance, and it says so in the language of a theory that has never yet been caught getting anything wrong. I think this is the real reason black holes occupy the position they do in our imagination, and I do not think it is the crushing. Everyone talks about the crushing, the stretching, the tidal forces, the grim mechanics of it. But we know how to think about being crushed. We have been thinking about being crushed for as long as there have been rocks and cliffs. What we do not know how to think about is a form of ending that leaves nothing behind, in a universe that has never once, anywhere, in any circumstance we can observe, left nothing behind. And here is the part that ought to bother you most. The universe is manufacturing these things, continuously, out of ordinary stars by an entirely ordinary process. A star lives its life, exhausts its fuel, fails to hold itself up, and the outcome of that completely routine sequence of events is a region where the road runs out. There is nothing exotic about the ingredients. It happens somewhere in the observable universe several times a second. There is a strange asymmetry in how we react to that too. We are perfectly capable of contemplating the heat death of the universe over a cup of tea. It is a much larger catastrophe by any accounting. It takes everything, everywhere, and leaves a cold, thin darkness with nothing in it. And yet it does not produce the same reaction, and the reason is that it leaves the clock running. There is a universe afterwards. It is empty and pointless and dark, and it is a universe, and something could in principle happen in it even if nothing ever does. That turns out to be the whole difference. We can accept the loss of everything as long as we do not lose the afterwards, which suggests that what we are actually attached to is not the contents of the world, it is the fact that there is a next. Physicists have been living with this prediction for 60 years, and the notable thing, if you read what they have actually written about it, rather than what gets said in documentaries, is that almost none of them have ever been comfortable with it. Not because it is frightening. Physicists are not squeamish. They are uncomfortable because it is unlike anything else their equations do. Every other prediction their equations make is a statement about what the world is doing. This one is a statement that the world stops doing. It is one of the two reasons the search for a quantum theory of gravity has the urgency it has. The other reason is a technical mismatch between two mathematical frameworks, and it is important, but it is a professional problem. This one is not professional. This one is somebody looking at the best description of reality we have ever produced and saying, I do not think that can be right, and I would like to know what is actually there. But before we get to what might actually be there, I want to hand this problem to a completely different group of people. Because physicists did not discover that the end of time is a paradox. They were about 23 centuries late to it. Philosophers got there first, and the version of the problem they found is in some ways worse, because it does not depend on any particular theory of gravity being correct. It does not depend on physics at all. It comes from the words. Part 5. The argument that is older than the physics. Try to say it out loud. Time ends. Now try to say what that means without cheating. It means there is a last moment. And what makes a moment the last one? Nothing comes after it. But after is a temporal word. You have just used the thing you claim to be abolishing in order to describe abolishing it. It is like trying to describe the edge of space by saying there is nothing beyond it, where beyond is a spatial word that requires the very thing you are denying. This is not wordplay, and it is not a trick, and it is not something modern philosophers invented to be difficult. It is the oldest problem in the subject, and the first person to state it clearly did so about 2,350 years ago. Aristotle put it in the Physics, and his version is beautifully economical. Every now, he says, is two things at once. It is the end of what came before, and the beginning of what comes next. That is not an observation about nows. That is what a now is. It is a boundary, and a boundary has two sides. So consider the proposed last moment. For it to be last, it would have to be an end without being a beginning. But an end that is not also a beginning is not a moment at all. It is a description of nothing, and notice that the argument runs equally well in the other direction. A first moment would have to be a beginning without being an end, which is the same impossibility wearing different clothes. Aristotle concluded that time is unbounded in both directions, not because he had measured anything, and not because he had a cosmology, but because he thought the alternative was incoherent. He was not making a claim about the universe. He was making a claim about what the word can be made to mean. 2,000 years later, Immanuel Kant took the problem seriously enough to build a piece of his philosophical architecture around it. In 1781, in the Critique of Pure Reason, he set out 4 what he called antinomies of pure reason, and the very first one is this exact question. He states a thesis. The world has a beginning in time. He gives an argument for it that appears to work. Then he states the antithesis. The world has no beginning in time, and he gives an argument for that which also appears to work. An antinomy, in Kant's technical sense, is precisely this situation. A question on which reason generates 2 contradictory answers, each of which seems sound with no available tiebreaker. It is not a puzzle awaiting more information. It is a place where thinking itself produces a contradiction. Kant's own diagnosis was that the question is malformed. We are trying to reason about the universe as a completed whole, and the whole is never actually given to us. We only ever get the parts. Ask the wrong kind of question, and you get 2 right-looking answers, which is the signature of a bad question rather than a hard one. It is worth hearing both of Kant's arguments, because they are short and they are both irritatingly persuasive. For the thesis, if the world had no beginning, then an infinite series of events has already been completed up to this moment. But an infinite series is by definition one that cannot be completed. Therefore there must have been a beginning. For the antithesis, suppose there was a beginning. Then before it there was empty time, and in empty time one moment is exactly like every other, so there is nothing to distinguish the moment at which the world started from any other moment. Nothing could have singled it out. Therefore there was no beginning. 2 arguments, 10 lines each, pointing in opposite directions, and each one making the other look careless. There is also a spatial twin to this antinomy, which Kant sets out immediately afterwards, whether the world is bounded in space, and it comes out to the same draw for the same reasons. That symmetry is worth noticing, because it tells you the trouble is not specifically about time, it is about limits as such. Whenever we try to reason about the edge of everything, our concepts fail in a characteristic and repeatable way, and they fail identically in both directions. Whether or not you accept Kant's resolution, and plenty of people do not, the diagnosis has aged remarkably well. The end of time is not an ordinary open question waiting on better instruments. It has the specific structure of a question that argues with itself. It is worth noting that somebody had already found the escape hatch, 1,300 years before Kant and long before anybody could have imagined general relativity. Augustine, in the 11th book of the Confessions, deals with a heckler's question. What was God doing before he made the world? And Augustine's answer is not theological, it is structural. There was no before, he says, because time was made along with the world. A first moment does not require a prior moment if time itself begins with it. That is, almost exactly, the move that 20th century cosmology would eventually make, arrived at by a man in North Africa in the 4th century with no equipment whatsoever. The modern version of the hard line belongs to Richard Swinburne, a philosopher at Oxford, and he does not hedge. It is not logically possible, he says, for time to have an end. His reasoning is a tightened version of Aristotle's. Any period of time that has a beginning must have been preceded by some other period, because a beginning is a boundary, and a boundary requires something on both sides of it. Run that argument in both directions and time comes out necessarily unbounded. Infinite in the past, infinite in the future, not as a matter of observation but as a matter of logic. Now stop and notice what that would mean. If Swinburne is right, then general relativity is not describing something disturbing. It is describing something impossible. And a theory that predicts an impossibility is not a theory that has found a strange truth about the universe. It is a theory that is wrong somewhere. That is one horn of the problem, and it is genuinely uncomfortable, because general relativity is not a shaky theory that we could set aside without much loss. It is the most precisely confirmed description of gravity anybody has ever produced. But here is what almost nobody tells you, and it is the reason this is a paradox rather than simply an error. The other horn is no more comfortable. Suppose Swinburne is right and time really is unbounded. Then the universe has existed for an infinite duration, and infinity has its own unpaid bills. Physical systems become more disordered as time passes. That is about as reliable as any statement in science. So if the universe has already been running for an infinite length of time, it has had infinite time in which to become as disordered as it can possibly get. Why has it not? Why are there still stars burning? Why is there still a gradient anywhere for anything to exploit? Why is anything at all still happening? A universe with an infinite past should be a universe in which nothing interesting has been possible for an infinitely long time. And instead we find ourselves in one that looks, by every measure we have, remarkably young and remarkably full of unspent order. An infinite past is not a free lunch. It has to explain why the universe looks like it just started. And that is why Kant filed this under antinomies rather than under mistakes. It is not that one side is right and the other is confused. It is that both sides have a bill they cannot pay. Time cannot end because the word will not let it. Time cannot be infinite because the universe would already have run down. And here we are, in the middle, in a universe that appears to be doing both. Aristotle had a distinction that explains why this refuses to resolve, and it is worth a sentence. He separated potential infinity from actual infinity. An unbounded future can be merely potential. You can always add another moment, without there ever being an infinite collection of them. But an unbounded past has to be actual. The moments are already there. They have already happened. And an actually infinite collection of completed events is a very different sort of claim from a promise that you can always keep counting. That distinction had a long and heated afterlife. Medieval philosophers in both the Christian and Islamic traditions fought over it for centuries, and the argument that an actually infinite past is impossible, that you cannot have finished counting an endless series, was the backbone of an entire tradition of cosmological argument. It has been revived in the 20th century and it is still being argued about now. I'm not going to adjudicate it, and I mention it only to make a point about the shape of tonight's subject. This is one of the very few questions on which a modern cosmologist and a medieval theologian would recognize each other's difficulties immediately, without needing anything translated. 23 centuries of extremely intelligent people have worked on this, and in all of that time nobody has produced a way of saying that time stops, which does not immediately use the word afterwards. That is not a failure of vocabulary, that is the shape of the problem. But physics does have something the philosophers did not have. It has a specific, concrete, technical suspicion that the whole thing might be a mirage, that the infinity in the equations was never in the world at all, and that we have seen this exact kind of mistake before and cleared it up. Part 6. Dividing by zero. There is a way of reading everything I have just told you that dissolves the horror entirely, and I want to give it full weight, because it is what most working physicists actually believe. The reading is this: the infinity is not out there. It is in the equations, and it is not a discovery. It is a symptom. Look at what the mathematics is actually doing. General relativity says that at the Big Bang singularity, all the material that would eventually become every galaxy we can see tonight, 2 trillion of them, more galaxies than there are seconds in 50,000 human lifetimes, was compressed into a single mathematical point, a point with zero size. Inside a black hole, the same thing. Everything that falls in is squeezed into a region of zero volume, and in both cases, when you go to calculate the density, you are asked to take a finite quantity of stuff and divide it by zero. The answer that comes back is infinity, and that is not a physical result. That is what a formula does when you push it outside the range of situations it was built to describe. It is the mathematical equivalent of a smoke alarm. Let me show you the cleanest example of this, and it is not cosmological at all. It is something you can do on a bright afternoon with a magnifying glass. Hold it up. Angle it. Find the sun. There is that moment of hunting where the bright blur on the paper shrinks and shrinks, and then suddenly you have it, and there is a hard little point of light with a wisp of smoke curling up out of it, and if you hold your hand steady, the paper browns and then blackens and then catches. Now, the theory of optics you were taught in school, light travels in straight lines, lenses bend them, the bent rays meet at a focus. That theory says something very specific about the spot you're looking at. It says that a perfect lens gathers light from a distant source and brings it to a single mathematical point, a point of zero area, which means a point of infinite intensity. Look closer, there is no such point. What is actually on the paper is a small, bright disk surrounded by faint concentric rings, like a tiny bullseye. About 84% of the light is inside the central disk, the rest is out in the rings. The pattern has a definite size. It is set by the wavelength of the light and the size of your lens, and its intensity, while certainly high enough to set fire to things, is always, in every case, finite. The pattern has a name, incidentally. It is called the Airy pattern, after George Biddle Airy, the astronomer royal who worked out the mathematics of it in 1835, and it turned out to matter enormously because it is the reason telescopes have the sizes they do. Two stars close together in the sky can only be told apart if their bullseyes do not overlap too badly, and since the size of the bullseye depends on the width of your mirror, the only way to see finer detail is to build something bigger. Every large telescope ever constructed is, in a sense, a monument to the fact that the infinitely bright point does not exist. If it did, a lens the size of a coin would resolve the universe. The infinity vanished, and it vanished for a reason that has nothing to do with better lenses. It vanished because light is not a ray. Light is a wave, and a wave cannot be concentrated more tightly than its own wavelength allows. Ray optics was never wrong about eyeglass prescriptions or funhouse mirrors or setting paper alight. It was wrong about one thing only. It did not know its own limits. When it produced an infinity, it was not describing an infinitely bright point in the world. It was announcing where it stopped applying. That, most physicists believe, is exactly what a gravitational singularity is. The late Lawrence Sklar spent a career at the University of Michigan thinking about the philosophy of physics, and he made the point about as carefully as it can be made. The physics of singularities remains genuinely uncertain and open to interpretation, and the theory that produces them is itself suggesting that they may not really exist. The late James Hartle, at the University of California, Santa Barbara, a man sometimes called the father of quantum cosmology, put it more bluntly. Most physicists, he said, would agree that these singularities are where the theory breaks down, not a discovery, a diagnosis. And if that is what is going on, the shape of the fix is already known. Quantum mechanics tells us that matter, like light, has wave-like properties. Every particle has a wave nature. That is not speculation. It is the foundation of a century of chemistry and electronics. So a genuine quantum theory of gravity ought to do to the singularity exactly what wave optics did to the focal point. It should blur it. The point becomes a small bundle. The bundle has a size. The division by zero never happens. The density comes out enormous, unimaginably, absurdly enormous, but finite. And if the density is finite, then the equations do not break. And if the equations do not break, then time does not end. That is why the search for quantum gravity has always had something of the character of a rescue mission, rather than a research program. It is not only about unifying two mathematical frameworks for the elegance of it. Part of the motivation, spoken and unspoken, has always been the hope of making the singularity go away. There is good precedent for that hope. At the end of the 19th century, classical physics predicted that a hot object should radiate an infinite amount of energy at short wavelengths, a result so obviously wrong that it acquired the name the ultraviolet catastrophe, and it went away. Max Planck in 1900 found that if you assume energy comes in discrete packets rather than a continuous stream, the infinity cancels and the answer matches the measurement exactly. That single assumption started quantum mechanics, so there is a very famous case of physics predicting an infinity, everyone assuming nature would sort it out, and nature sorting it out. There is a second precedent, and it is more ambiguous, and honesty requires mentioning it. In quantum field theory, calculations kept producing infinities, and the technique that emerged for handling them, renormalization, does not actually remove them. It absorbs them into quantities that get measured experimentally rather than calculated. It works spectacularly. The theory of the electron's magnetic behavior is confirmed to something like 12 decimal places. And Paul Dirac, who did as much as anyone to build the field, went to his grave calling it a fudge. Sometimes infinities are cured, sometimes they are just filed away where they cannot embarrass anybody. It is also worth saying that not every singularity in general relativity involves infinite density. Some are singular in the curvature, some in the tidal forces, some only in the technical sense that paths cannot be extended even though every measurable local quantity stays finite. That variety is itself a small piece of evidence for the symptom reading. If singularities were genuine objects, you would expect them to have a consistent character. They do not. They look much more like the several different ways a description can fail than like several different kinds of thing. And modern physicists are not, by temperament, frightened of infinity in the way Aristotle and Kant were. Infinite sets are ordinary mathematics now. Nobody flinches at them. What has survived is something more useful than fear, an instinct, learned the hard way over about a century, that a physical infinity is a warning label. It is not a result. It is the theory telling you where it stops being your friend. The scale where the blurring is expected to happen is worth stating, because it explains why nobody has checked. It is called the Planck length, and it is about 10 to the minus 35 meters. To get a feel for that, if you took a single proton and blew it up to the size of the observable universe, the Planck length would still be smaller than a grain of sand. Nothing we can build, and nothing we can imagine building comes anywhere close. The relevant timescale, the Planck time, is the time light takes to cross that distance, and it is roughly 10 to the minus 43 seconds. There is one more thing worth noticing about the magnifying glass, and it is the thing that will matter later. The reason the point does not exist is not that our lenses are imperfect. A flawless lens ground by a god would still produce a bullseye. The limit is not in the instrument, it is in what light is. And that is the uncomfortable half of the analogy, because if the singularity is like the focal point, then the thing that removes it will not be a better theory of gravity. It will be a discovery that gravity or space or time is not the sort of thing we have been assuming it is. So here is where we have arrived, and I want you to enjoy it for a moment, because it is the last comfortable ledge on this climb. The end of time may well be a mirage. It may be the smoke alarm going off in a theory that has walked past its own boundary, and behind the alarm there may be nothing more alarming than a very small, very dense, entirely ordinary object. That is the reassuring version. I have given it to you honestly and completely, because it deserves to be taken seriously. Now let me tell you why it does not work. Part 7. Where we actually are. Let us stop for a moment and put the pieces on the table together, because we are about halfway through and the second half goes somewhere the first half does not prepare you for. Here is what we have. We have a theory of gravity that is not a candidate and not a proposal. General relativity has been checked against the orbit of Mercury, against the bending of starlight, against the ticking of clocks in towers and on aircraft and in orbit, against the slow decay of binary pulsars over decades, and against the ripples in space-time produced by black holes colliding 1 billion light-years away. It has never been caught being wrong, and that theory says, without hedging and without apology, that under conditions this universe is known to produce routinely, time comes to an end. Not slows, ends. And it says so not as a peculiarity of some idealized solution, but as something forced. Penrose proved it, Hawking extended it, and the Nobel Committee eventually agreed. Against that, we have an argument that predates the theory by 23 centuries and does not depend on it. The end of time may not be a describable state of affairs at all. Aristotle showed that a moment which is only an end is not a moment. Kant showed that reason produces contradictory proofs about it. Swinburne says flatly that it is not logically possible, and their argument has no obvious hole in it, because it is not about physics. It is about whether the sentence means anything. We also have a strange structural fact that we have not really digested yet, and it will come back. The end of time does not have to be a universal event. Relativity permits it to be a local one, a region where world lines terminate, sitting quietly inside a universe where everything else carries on. That is not how anybody's imagination works. When we picture the end of time, we picture a last tick, everywhere, all at once, like a hall of clocks stopping together. The theory says it can be a much more intimate affair than that, and that it is probably happening somewhere in this galaxy right now, and that nothing about it will ever reach us. We have a very plausible way out, which is that the infinity was never real, that the singularity is a smoke alarm, not a fire, that when we finally have a quantum theory of gravity, it will blur the point into a bundle the way wave optics blurred the focus into a bullseye, and everybody will wonder what the fuss was about. There is precedent for that. There is also a precedent in renormalization for infinities getting swept under a rug rather than removed, and so the whole weight of the problem comes to rest on quantum gravity. Fix the singularity, and time does not end, and Aristotle keeps his argument, and Einstein keeps his theory, and everybody goes home. Here is the turn, and it is the thing I want you carrying into the second half of tonight. There are two serious ways quantum gravity could resolve this, and they are not variations on a theme, they are opposites. One says time really does end, and we simply need a completely new kind of law to describe an ending, a law that does not talk about change at all. The other says time never ends anywhere, that the Big Bang was a transition rather than a start, and that nothing is ever finished, and both of them work. That is the problem. Both of them are internally consistent, both have serious people and serious mathematics behind them, and both of them charge admission at the door. Because it turns out that you cannot get out of this contradiction for free. Nobody has yet found a version of quantum gravity that saves time without surrendering something else that we had assumed was not negotiable, and the surrendered thing is different in each case, which is why the argument has never settled. Each escape route requires you to give up something that physics has assumed for centuries, or something the universe appears to require in order to look the way it looks. The rescue is not a repair, it is a trade, and there is a third possibility that is not a compromise between them, which we will come to later, and which I think is the most interesting idea in the whole subject. It says that the argument between the two camps has a hidden assumption inside it, shared by both sides, and that once you take that assumption out, the paradox does not get solved. It stops being a paradox and becomes something stranger and considerably more beautiful. But that one has to wait, because it only makes sense once you have seen the other two fail on their own terms. So let us go and look at the price of each one, and we will start with the branch that most people find hardest to take seriously, which is the branch where the equations mean exactly what they say, where time genuinely, finally stops, and physics has to learn a new language in order to say so. Part 8. A law with no time in it. Suppose the equations mean exactly what they say. Suppose time really does terminate at a singularity, and there is no repair coming. The first consequence of that is not philosophical. It is technical, and it is severe, and once you see it, you cannot unsee it. Every law of physics we possess is a law about change over time. Think about that inventory for a second. Newton's second law tells you how a force changes an object's motion from one instant to the next. Maxwell's equations tell you how electric and magnetic fields evolve. The Schrödinger equation tells you how a quantum state develops. Einstein's own field equations, in the form physicists actually use to calculate things, tell you how the geometry of space-time unfolds from one slice to the next. Every single one of them has the same shape. You hand the law a description of the world at one moment, and it hands you back a description of the world at the next moment. Physicists have a name for this shape. They call it an initial value problem. Give me one slice, and I will give you every other slice forwards and backwards for as long as you like. Now try to feed an ending into a machine built like that. You cannot. The machine does not have an input for it. Ask any of those laws what happens at the last moment, and they will dutifully tell you what happens next, because telling you what happens next is the only thing they know how to do. There is no way to write the sentence. There is no next in a language whose entire grammar is about what comes next. So a genuine endpoint of time cannot be described by any law of the kind we currently use. It would require not a new law, but a new kind of law, something that does not mention motion, or change, or evolution, or any of the vocabulary that has served physics since the 1600s, something that makes its statements in terms that are, in the proper sense, timeless. It is worth pausing on how radical that is, because it does not sound radical when you say it quickly. Physics has spent 4 centuries becoming extraordinarily good at one specific trick, describing how things change. That is the whole game. Galileo rolling balls down inclined planes was measuring change. Kepler's orbits are change. Thermodynamics is change. Even the parts of physics that look static, the conservation laws, the symmetries, are really statements about what stays the same while everything else changes, which means they are still statements about a process unfolding. If you take away change, you have not removed a chapter from the textbook. You have removed the thing the textbook is written in. There is one obvious candidate, and it has been sitting in mathematics the whole time: geometry. A geometric law does not tell you what happens next. It tells you what shapes are permitted. It says, a thing of this kind must have these properties, not because a process produced them, but because nothing of that kind can be otherwise. There is no before and after inside a theorem about triangles. The theorem simply holds. Brett McInnes, a mathematician at the National University of Singapore, has developed a proposal along exactly these lines, and he built it out of string theory. His suggestion is that the early universe had the topology of a torus, a donut. Not donut-shaped in the sense that you could hold it, but with the connectivity of a donut, a space that wraps around on itself in a particular way. Why does that matter? Because there are mathematical theorems about tori which force any such space to be, in a specific technical sense, perfectly uniform and smooth. That is not a result you derive by watching the universe evolve. It is a result you derive from the shape. The universe was smooth at the beginning on this picture, not because some process smoothed it, but because a space with that topology cannot be anything else. That is a genuinely different kind of explanation, and it is worth sitting with. Every explanation you have ever been given for anything in physics is a story about a process. This is not a story. There is nothing that happens. There is only a constraint, and the universe satisfies it in the way a triangle satisfies the theorem about its angles. I should say, in passing, that people have tried before to write down a fundamental equation of the universe with no time in it. There is a famous one from the 1960s, and the trouble it caused is so well known that it has its own name. Physicists call it the problem of time, and it has been a running sore in quantum gravity for 60 years. I have talked about that at length before, and I am not going to reopen it tonight. I mention it only so you know that this is not an eccentric idea. It is a direction physics has been pushed in repeatedly, and always reluctantly. Now here is the payoff of McInnes's proposal, and it is the most startling idea in this half of the story. At a big crunch, or at the singularity inside a black hole, those theorems do not apply. The conditions that force smoothness at the beginning are simply not present at the end, which means the universe, at its termination, could take on any shape at all. It could be arbitrarily wildly irregular. There is no constraint waiting there to tidy it, and that means a geometric law of this kind is not symmetric in time. Stop and feel the weight of that, because physics has been assuming the opposite for 400 years. The standard picture is that the laws themselves are perfectly even-handed about direction, and that every asymmetry we observe, the fact that cups smash rather than reassemble, the fact that we remember yesterday and not tomorrow, comes from the initial conditions, from how things happen to be set up at the start. The laws do not care, the starting arrangement does. McInnes's proposal moves the asymmetry into the law. The constraint operates at one end and not the other. The end is not the beginning played backwards. It bears no resemblance to the beginning at all, and it does not because the rule that made the beginning what it was is not there. Penrose, incidentally, arrived at something structurally similar by a completely different route, a proposal called the Weyl curvature hypothesis, which requires a particular measure of the distortion of spacetime to vanish at initial singularities, but places no such requirement on final ones. Two very different mathematical instincts, converging on the same strange conclusion. Whatever is going on, the two ends of time are not mirror images. There is one more feature of this idea that I think is underappreciated. Notice that it does not make the end of time less real. It makes it more real. Most attempts to deal with a singularity are attempts to get rid of it, to show it was an illusion, an artifact, a smoke alarm. This one accepts the singularity at face value and instead rebuilds the notion of a physical law around it. That takes a certain kind of nerve. It is the difference between arguing that the hole in the road is a trick of the light and simply admitting there is a hole and redesigning the vehicle. And it has a testable flavour, at least in principle, which not every idea in quantum gravity does. If the smoothness of the early universe follows from topology rather than from a process, then the details of that smoothness, the precise statistical character of the tiny ripples we see imprinted on the oldest light in the sky, ought to carry a fingerprint of the shape rather than of a mechanism. Nobody has found such a fingerprint, but it is the kind of thing that could in principle be looked for, and that alone puts the proposal in better company than a good deal of what gets written about the end of time. So what does this branch cost? It costs the assumption that the laws of physics are laws about change. That is not a small tax. It is the founding assumption of the entire subject, the thing that separated Galileo from everyone before him. In exchange, you get a universe in which time really can have an edge, because you finally have a kind of law that can describe an edge without needing something on the other side of it. It is, in a way, Kant's thesis handed a mechanism. The world has a beginning in time, and now there is a shape that explains why, and an explicit reason why the same explanation refuses to run at the far end, which is elegant. And there is an entire camp of physicists who think it is completely unnecessary, because in their view, nothing ever ends at all. Part 9. The branch where nothing ends. The other camp looks at the same problem and reaches the opposite conclusion. Time, they say, stretches endlessly in both directions. It has no beginning and it has no end. And the Big Bang, that great founding event that everybody has heard of, was not the start of anything at all. It was a transition, a very violent one, admittedly, but a transition in the ongoing life of a universe that was already there. The picture goes like this. Run the clock backwards. The universe contracts, the density climbs, and at some point before the density can become infinite, before the equations break, quantum effects become important and they push back. The contraction slows, stops, and reverses. What we call the Big Bang was the moment of rebound. A big bounce rather than a big bang. I want to be clear that this is not a hopeful sentiment somebody had in a bar. It is a calculated result inside at least one serious framework. In 2006, 3 physicists, Abhay Ashtekar, Tomasz Pawlowski, and Parampreet Singh, published work in a field called loop quantum cosmology, showing that, within their particular way of quantizing gravity, the universe does not reach a singularity. It bounces. The story goes that Ashtekar was so wary of the result that he asked his colleagues to spend 6 months trying to break it before he was willing to publish. Martin Boyewald had laid much of the groundwork the year before. It is worth appreciating how ancient this idea is, and how thoroughly it has been reinvented. Cyclic cosmologies are not a modern invention. Nearly every culture that thought seriously about time arrived at some version of the wheel, of endings that fold back into beginnings. What is different now is that this version came out of a calculation rather than out of an intuition. Nobody was trying to get a bounce. They were trying to quantize gravity, and the bounce fell out. That is the sort of thing that makes physicists pay attention. When a picture you were not looking for arrives uninvited in the middle of somebody else's equations. The reason it bounces is worth knowing, because it is very concrete. In loop quantum gravity, space is not infinitely divisible. Area and volume come in discrete quanta. There is a smallest possible chunk. And if there is a smallest possible chunk of volume, then there is a maximum possible density, because you cannot keep squeezing something into less space than the smallest available space. When the universe approaches that ceiling, gravity effectively turns repulsive. The collapse becomes a rebound, not because anything pushed, but because there is nowhere left to fall into. If that is right, then there was a universe before ours, and it was contracting, and everything in it came through the bounce and became everything in this one, and traces of that era might in principle still be with us tonight, faintly imprinted on the oldest light in the sky. Although Boyewald himself found a limit on that hope, a result sometimes called cosmic forgetfulness, showing that some information about the previous era is irretrievably scrambled by the passage through, so that even in the best case we could only ever recover fragments. Now apply exactly the same logic to a black hole. If the singular point is really a small dense bundle rather than a mathematical point, then the core of a black hole is not an ending, it is an object, and in some treatments it is a remarkably lively one, a bundle that behaves like a miniature star, boiling and bubbling and doing things rather than a full stop, which changes what happens to you if you fall in. It is still a painful and comprehensive end. Nobody is offering survival here. But your timeline does not terminate. Your particles enter the bundle, and they leave a distinct mark on it, a specific particular disturbance that is yours and nobody else's. And because black holes are not permanent, because they slowly radiate their mass away as an extraordinarily faint glow over unimaginable spans of time, that mark might in principle be readable. Some future observer, patient beyond any meaning of the word, could in principle detect the imprint of everything that ever fell in, encoded in the light coming out. You would not survive, but you would leave a trace, and there would be a universe in which the trace existed, which is, in the strange accounting of this subject, an enormous improvement. And a black hole that is an object rather than an ending has one more consequence that is easy to miss. It means the interior has a history. Things happen in there. There is a sequence of events inside the bundle, a before and an after, states following one another, which is to say that time has not stopped at all. It has simply become extremely strange and extremely compressed and completely unreachable from where we are sitting. The end of time turns out to have been a failure of our mathematics to follow, not a failure of the universe to continue. That is the promise of this branch, stated as generously as I can state it. The great advantage of this branch is that it requires nothing new, no exotic new category of law, no abandonment of 4 centuries of assumption. Everything stays as it is. There is simply no edge anywhere. The disadvantage is that it inherits 2 very old problems, and neither one is close to being solved. The first is entropy, and it is the bill we already saw the philosophers hand to Aristotle. Physical systems become more disordered as time passes. If the universe has been running for an infinite length of time, it has had infinite time in which to become as disordered as it possibly can. So why is it not? Why are stars still burning? Why is there still a temperature difference anywhere between anything and anything else? Why has the coffee not finished cooling? Look around at the night sky, and you're looking at a universe that is manifestly not finished. Stars are forming right now in the Orion Nebula and 10,000 places like it. That is a universe with unspent order in it, and a universe with unspent order after an eternity is like walking into a house you have been told has been on fire for 1,000 years and finding the furniture intact. Ludwig Boltzmann, who first understood the statistical origin of the arrow of time, proposed an answer to this in the 1890s, that the universe as a whole is in equilibrium, and that we live inside a rare random fluctuation, a temporary pocket of order in an endless sea of disorder. It is a clever answer, and it collapses under its own weight. If you're going to appeal to random fluctuations, then a fluctuation that produces a single conscious brain with false memories of a whole universe is astronomically more likely than a fluctuation that produces an entire, ordered cosmos containing that brain. So the theory predicts that you are overwhelmingly likely to be a momentary hallucination assembled out of noise. Most physicists treat that not as a result, but as a demonstration that something in the assumptions is broken. There is a version of the entropy objection that is even harder to shrug off, and it is worth a moment because it applies to the bouncing picture specifically. If the universe bounced, then whatever was in it before the bounce had its own entropy, and entropy does not go down, so the pre-bounce universe must have been more ordered than ours is, and the one before that more ordered still. And if you run that chain back infinitely far, you need an infinitely ordered starting point, which is precisely the beginning the whole picture was invented to avoid. Some versions escape this by having the universe grow larger with each cycle, spreading the entropy thinner. Others accept it and look for a mechanism to reset the ledger at each bounce. None of the escapes is agreed on, and the objection is old enough to have a pedigree. Richard Tolman raised essentially this point against cyclic cosmology in the 1930s, and it has outlived every proposal made since. The second problem is escape, and it is sharper. If your imprint survives inside the bundle at the black hole's core, it has to get out, and it has to get out through the one object in the universe whose defining characteristic is that nothing gets out of it. That is the black hole information problem, and it has been open since Stephen Hawking raised it in 1976. Quantum mechanics insist that information is never destroyed, that in principle the past is always recoverable from the present. General relativity insists that anything crossing a horizon is gone. Both cannot be right. Hawking eventually conceded the argument in 2004 at a conference in Dublin and paid off a bet with a baseball encyclopedia. It made headlines. What the headlines mostly did not mention is that he conceded the conclusion without supplying a mechanism. He came to believe the information gets out. Nobody, then or now, can say how. So both branches are on the table, and both are leaking. One says time ends and asks you to invent a new kind of law. The other says time never ends and cannot explain why the universe still has anything left to burn, or how anything that falls in ever comes back out. Somebody stated this whole predicament in a single sentence decades ago, and it remains the best summary anybody has produced. Part 10. Wheeler's Sentence. John Archibald. Wheeler is not a household name, and he should be. He is the man who took general relativity from being a beautiful mathematical curiosity that almost nobody worked on in the 1940s and turned it into a living field. He popularized the term black hole. He coined wormhole. He coined quantum foam. He supervised Richard Feynman and Kip Thorne and Hugh Everett, who came up with the many worlds interpretation of quantum mechanics as a graduate student under him. Wheeler spent decades on the problem of how to marry gravity to quantum theory, which means he spent decades staring directly at the thing we have been circling all evening. Wheeler had a way of compressing things that came from a lifetime of teaching, and he had a phrase for what he thought this particular difficulty amounted to. He considered the collapse of the geometry itself to be the greatest crisis in physics, greater, in his view, than anything quantum mechanics had thrown at anybody. That is a considerable claim from a man who had watched quantum mechanics dismantle the entire classical picture of matter in his own lifetime. His reasoning was that quantum mechanics had overturned what things are, whereas this overturns whether there is a stage for them to be on. And near the end of his life he wrote the cleanest statement of it that anybody has managed. Einstein's equation says this is the end, and physics says there is no end. That is the paradox. That is the whole thing, in 14 words, with no mathematics in it at all. It is worth saying who else has stood where Wheeler stood, because it is not a small crowd, and it is not a fringe one. Einstein himself never accepted that the singularities in his own theory were physically real, and spent effort trying to argue them away. Eddington called the idea of a star collapsing to a point a reductio ad absurdum, and suggested that some law of nature must intervene to prevent it. Landau, in the Soviet Union, reached the same conclusion independently, and was equally unwilling to believe it. For roughly 40 years, the standard professional attitude toward the singularity was that it was somebody else's problem and would sort itself out. What Penrose did in 1965 was make that attitude untenable, and what Wheeler did was find the words for how uncomfortable the new position was. I want to point out how unusual the shape of that is, because it is easy to hear it as an ordinary scientific disagreement, and it is not one. Ordinary scientific disagreements are about numbers. Two teams measure the expansion rate of the universe and get answers that do not agree, and everybody argues about systematics until somebody sorts it out. That is normal. That is how the field works. This is not that. This is a disagreement between our single best description of gravity and the general grammar of every other law we have, and I want to stress how strong the first side of that is, because it is tempting to assume that when a theory predicts something absurd, the theory is on shaky ground. General relativity is not on shaky ground. It explained the precession of Mercury's orbit, an anomaly that had defeated astronomers for half a century. It predicted the bending of starlight by the sun, which has since been confirmed by radio interferometry to better than 0.01%. It predicted that a pair of neutron stars orbiting each other would lose energy to gravitational waves and spiral inward, and the Hulse-Taylor binary pulsar has been doing exactly that, matching prediction to about 1 part in 1,000, continuously for 50 years. And in 2015 we finally heard the waves themselves, the ringing of space-time as two black holes merged more than 1 billion light-years away, arriving at a pair of detectors in America as a rising chirp that lasted 1/5 of a second and matched the calculation almost perfectly. That is the theory saying time ends, not a sketch, not a first approximation, the most successful physical theory in the history of the subject, and on the other side is not a rival theory but something more diffuse and in its way more stubborn. The fact that every other law we have is written in a language that has no way of expressing the sentence. It is not that quantum mechanics contradicts the claim, it is that quantum mechanics cannot state it. Faced with this, the community splits, and neither half is being unreasonable. One group concludes that we have run into a genuine limit, not a temporary gap that better instruments will close, but a boundary, that the edges of time are also the edges of what reason and observation are capable of reaching, and that this question may simply never be settled by science, because it is not the kind of question science can be pointed at. That view has a long and respectable pedigree, and it connects to arguments we will meet later about whether a quantity nobody can measure even in principle is a real quantity at all. The other group is unmoved. Gary Horowitz, at the University of California, Santa Barbara, a string theorist who received the American Physical Society's Einstein Prize in 2023 and the Dirac Medal in 2025, has said plainly that this question is not beyond what physics can reach, and that quantum gravity should be capable of providing a definite answer. Not a story, not an interpretation, an answer. Both positions are held by first-rate people. Neither has an argument that compels the other, and there is currently no observation anybody can propose that would settle it, because the relevant regime is roughly 20 orders of magnitude beyond the reach of any instrument that has ever existed or been seriously designed. There is a particular flavour of frustration in that, and I think it is worth naming, because it explains something about how this subject gets talked about. In most areas of science, when you reach the edge of what is known, you can at least describe what an answer would look like. You could say, if we built a detector this sensitive, or if we found a fossil of this age, or if this number came out above that threshold, we would know. Here, nobody can finish that sentence. There is no experiment on anybody's whiteboard that would distinguish a universe where time ends from one where it does not. That is why the literature on this reads the way it does. Careful, hedged, and slightly haunted. These are people who are used to being able to say what would settle it. That is the situation. Not a cliffhanger, not a tease. That is genuinely where the subject stands tonight. And what I find quietly remarkable about Wheeler's sentence is how small it is. There is no equation in it. There is no jargon. Anybody can hold it in their head after hearing it once. 14 words, and you have the entire crisis. The difficulty was never in understanding the problem. The difficulty is that understanding it does not help. And notice one more thing about the standoff before we leave it. Both camps share an assumption so basic that neither one states it, that time is a single thing, which either continues or does not, yes or no, on or off. Everything we have covered so far, the equations, the antinomy, the branches, the bills, takes that for granted. It is the frame the whole argument is happening inside. But there is a third way of thinking about all this, and it does not sit in either camp, and I have been holding it back all evening because it only works once you have watched both of the obvious answers fail. It does not resolve the paradox. It does something more interesting than that. It takes the paradox apart and shows you that there was a hidden assumption inside it, one that both camps were making without noticing, and that once you remove that assumption, the question of whether time ends stops having a yes or a no. It has a schedule instead. Part 11. Twilight. Here is the assumption. Time is a thing, one thing, a substance, or something like a substance, which is either present or absent, either running or stopped. Take that away and everything changes. Think about life for a moment, because it is the best available analogy, and it is not a loose one. Life is not a substance. For most of human history, people assumed it was, that there was some vital fluid or animating spark, present in living things and absent in dead ones, and that dying consisted of the spark going out or the fluid draining away. That was a completely reasonable hypothesis, and it was wrong. Life is not a stuff. Life is what happens when inanimate molecules organize themselves into a sufficiently intricate arrangement. And when the arrangement comes apart, life stops. Not because anything left, but because the organization was what life was in the first place. Now suppose time is like that. Suppose a world with time in it is simply a world with a particular kind of structure. A structure that lets you say when things happen, how long they last, and in what order they occur. Time, on this view, is not imposed on the universe from outside. It emerges from within, out of whatever the underlying timeless substance turns out to be, in the way that temperature emerges from molecular motion. I want to be extremely careful here, because this is the exact point at which people leap to a conclusion that is not in the physics. Emergent does not mean fake. Temperature is emergent. There is no such thing as the temperature of a single molecule. Temperature is a statistical property of a large number of them, and yet you can be burned by it, and a thermometer works, and nobody has ever suggested that heat is an illusion. Wetness is emergent. Individual water molecules are not wet. The ocean still drowns people. When a physicist says time may be emergent, they are not saying you imagined this afternoon. They are saying time is made of something, the way water is made of something. And here is the consequence, which is the whole reason this reframing matters. What emerges can be disassembled. If time is a structure rather than a substance, then the end of time is not a wall. It is not a last tick followed by a nothing. It is a gradual loss of properties. Time shedding its defining features one at a time, until there is nothing left that deserves the name, not a cliff edge, a twilight. And the enormous advantage of this picture is that it makes the end of time no more mysterious than the breakdown of any other complex system. We know how to describe things falling apart. It is not a paradox for a building to be demolished, or an organism to decompose, or an ecosystem to collapse. The incoherent event becomes an ordinary process, and an ordinary process is something physics can talk about. And notice what this does to the paradox. Both camps were arguing about whether a single switch is on or off. If time is a bundle of separable properties rather than one thing, then the question changes shape entirely. It is no longer whether time ends, it is which parts of it go, and in what order, and whether what is left at each stage still deserves to be called time at all. That is not a yes or no question, it is a sequence. So if time comes apart in stages, which stage goes first? The answer is the one that we care about most, which is a bad sign for the rest of the evening. The first thing to go is the arrow, the one-way directionality, the fact that time points from past to future and not the other way around. And here is the thing that most people find genuinely surprising, even though physicists have understood it since the middle of the 19th century. That arrow is not a property of time itself. The fundamental equations do not have a direction in them. Film two billiard balls colliding, play it backwards, and nothing in the laws of motion is violated. You are watching a perfectly legal collision. The equations are indifferent. Film a cup falling off a table and smashing, play it backwards, and the reassembling cup is also, strictly speaking, legal. Every molecule is doing something permitted. It is simply absurdly, astronomically unlikely. The arrow is a property of matter, not of time. It exists because there are overwhelmingly more disordered arrangements available than ordered ones. So random rearrangement has a statistical direction, the way a shuffled deck has a direction. Anyone who lives with pets or small children has an intuitive grasp of this. There is exactly one configuration of your living room that counts as tidy, and effectively an infinite number that count as untidy, and so leaving the room alone has an outcome, which means the arrow depends entirely on there having been an ordered starting point. Something had to set the room up tidy at the beginning, and that is precisely the thing McInnes's torus was invented to supply. The smoothness of the early universe, forced by the topology rather than produced by any process, is where the arrow comes from. The two halves of tonight's story lock together right here. A geometric constraint at one end of time is what gives every subsequent moment its direction, which means it is what gives you the ability to remember this morning and not tomorrow morning. The arrow you are experiencing right now is being paid for by the shape of the beginning. Physicists have a name for the assumption when they cannot explain it, which is most of the time. They call it the past hypothesis. The universe simply began in an extraordinarily low entropy state, and everything follows. It is honest, and it is a placeholder rather than an explanation. Penrose once estimated how special that starting state had to be, and the number is 1 part in 10 to the power 10 to the power 123. That is not a number anybody can make intuitive. It is not the number of atoms in the universe. It is not the number of anything in the universe. There is not enough universe to write it in. Now run the arrow forward and see where it goes. If the trend continues, and there is no reason it should not, the universe eventually reaches equilibrium, heat death, the state in which it cannot become any more disordered, because there is no order left to spend. Individual particles keep moving. Nothing is frozen in the naive sense. But the universe as a whole stops changing. Every gradient has been flattened. Every difference has been paid out. There is a schedule for this, and it was worked out in remarkable detail by two astrophysicists, Fred Adams and Gregory Laughlin, in a long paper in Reviews of Modern Physics in 1997. Their timeline runs like this. Star formation, which is happening all around us tonight, effectively finishes somewhere around 100 trillion years from now when the gas runs out. Then comes an era of degenerate remnants. White dwarfs cooling, neutron stars cooling, the occasional collision. Then, over spans that make 100 trillion look immediate, even those disperse or decay, and the universe belongs to black holes. And then the black holes go too. A black hole the mass of the Sun takes roughly 10 to the 67th years to evaporate. The largest ones at the centres of galaxies take something closer to 10 to the 100th. For scale, the universe is currently about 10 billion years old. The ratio between now and the last black hole is not a large number in any ordinary sense. It is a number that breaks the ordinary sense of large. And one small detail from that schedule is worth carrying, because it is exactly the sort of thing this channel exists for. Nothing evaporates yet. A black hole colder than its surroundings absorbs more than it emits, and the cosmic microwave background is currently a little under 3 degrees above absolute zero, while a black hole the mass of the Sun is about 60 billionths of a degree. So the holes are still feeding faintly on the warmth of the Big Bang. They cannot begin to die until the universe has finished cooling around them. And here is the part that matters for tonight. Any clocks that remain will oscillate in both directions. Not because the mechanism has failed, but because there is no longer anything in the universe biased toward one direction rather than the other. The statistical thumb on the scale is gone. The distinction between future and past does not get abolished by decree. It blurs by exhaustion. Imagine that clock. Not metaphorically. Imagine actually being there. Everything is dark, and it has been dark for longer than the word long can carry. The last star burned out an unthinkable span ago. What remains is thin and cold and enormously spread out. A few dead cinders, some drifting particles, and black holes so isolated from one another that each might as well be its own universe. There is no light except the almost immeasurably faint glow leaking out of the holes themselves, colder than anything that has ever been cold. And somewhere in this, a clock, still running. You watch the pendulum. It swings and comes back and swings, and then it does not quite come back the way it went, and then it swings backwards twice in a row. Not because it is broken, because there is nothing left out there to tell it which way is forward. It is not a clock anymore. It is an object that moves, and the movement means nothing, and there is no one there to read it. And for the first time this evening, the absence of a witness feels less like a horror and more like a mercy. Some physicists have speculated that the arrow might then reverse, that the universe could begin tidying itself up, that the cup might reassemble. This gets presented in popular accounts as a hopeful scenario. It is not one. For any being whose existence depends on a forward arrow, a reversal ends time exactly as decisively as heat death does. You cannot form a memory in a universe running the other way. Memory requires the past to be more ordered than the present, which is the arrow, restated. And a creature that cannot form a memory is not experiencing time. It is being processed by it. So this is the first loss, and it is worth stating clearly what has gone. Every memory anyone has ever formed, every decision anyone has ever made, every sense that anything at all was happening rather than merely being, all of it is downstream of the fact that the early universe was smooth. Not downstream of a law, downstream of a shape. Change the shape and there is no yesterday to remember. The arrow was never something we owned. It was alone against the order of the beginning, and we have been spending it for 13.8 billion years, and it is only the first thing to go. Part 12. The universe without clocks. The second thing to go is duration, and the argument for it belongs to Roger Penrose, and it is the most surprising piece of reasoning in this entire subject. He sets it out in a book published in 2010 called Cycles of Time, and before I tell you what is in it, I want you to hold in your head who is making the argument. Penrose is the man who proved that time ends. The singularity theorems are his. The demonstration that they are generic rather than exotic is his. The Nobel Prize is his. He has argued for decades that matter falling into a black hole ceases to exist in any meaningful sense, and that time may play no role whatsoever in a genuinely fundamental theory of physics. If there is a single person responsible for the fact that physicists now accept the universe contains places where description terminates, it is him. Keep that in mind because of where this ends up. He starts at the beginning. Immediately after the Big Bang, the universe was not a structure. It was a disordered collection of particles, quarks, electrons, and the rest of the elementary inventory, like a box of interlocking bricks tipped out onto a floor with nothing yet assembled. Everything that would later exist, every atom and molecule and star and galaxy and person, would be built from that, in stages, one step at a time. The first significant step happened about 10 microseconds in, when quarks bound together into protons and neutrons. 3 quarks each bundle about 1 femtometer across, a millionth of a meter, which is to a grain of sand roughly what a grain of sand is to the distance from here to the moon. It is worth knowing what that moment at 10 microseconds actually was, because it is one of the genuine turning points in the history of everything. Before it, quarks moved freely. After it, they were permanently confined, bound into threes, never again to be found alone, in a condition that has held for 13.8 billion years and shows no sign of relaxing. We have recreated that free quark state briefly, in heavy ion collisions at Brookhaven and at the Large Hadron Collider, by smashing gold or lead nuclei together hard enough to melt the protons themselves for a few billionths of a second. It is the hottest matter ever made by human beings, several trillion degrees, and it is the closest anyone has come to visiting the era Penrose is describing. Before that moment, there were no composite structures at all. Nothing was made of anything. try to be there. There is no space in the sense you know it, no room, no landmarks. There is a scalding, seething uniform something, and there is not one object in it. Nothing is bound to anything. Clumps form and dissolve before they can be said to have formed. There is no smallest thing and no largest thing, no ruler, no reference, nothing that stays the same size while anything else changes. And in that condition, a question you have never once had to ask becomes unanswerable. How long has this been going on? There is nothing there to ask it of. That is the consequence almost nobody notices. There was no way to keep time. Because think about what a clock actually is. Every time-keeping device that has ever existed works on the same principle. It contains something that stays the same size while the world changes around it. A pendulum needs a length. A quartz watch needs a crystal of a particular dimension. An atomic clock needs the size of an electron's orbital. And in fact, the definition of the second itself is a statement about the size of a cesium atom, 9,192,000,000, and some hundreds of thousands of oscillations of a particular transition, which is only a fixed number because the atom is a fixed size. Every unit of time humanity has ever used is borrowed from the size of something. There is a small detail in that which I find quietly wonderful. The second is currently being redefined. For decades it has been pinned to cesium, but optical clocks, the ones that resolve a millimetre of height, are now so much better that the international standard is expected to be rebuilt around them sometime around 2030, after a 6-country comparison completed in 2025. And notice what that redefinition consists of. It is not a move toward measuring time more directly. There is no such thing. It is a move to borrowing the size of a different atomic transition instead. Every improvement we have ever made in timekeeping has been an improvement in our choice of ruler. We have never once measured time. We have only ever measured things that hold still. In the primordial soup there was no such thing. The clumps that formed had no fixed size, and could not serve as a standard. You might object that the particles themselves could do the job. They cannot. Quarks and electrons have no measurable size. Examined closely, to a particle physicist, they are points. The only size-like property they possess is something called the Compton wavelength, which sets the scale on which quantum effects matter. For an electron it is about 2.4 picometers, and which is inversely proportional to mass. And even that was unavailable before about 10 picoseconds after the beginning, because the process that gives particles their rest mass had not yet happened. No mass, no Compton wavelength, no length scale, no clock, and therefore, in a very literal sense, nothing to keep track of. Penrose's own phrasing is exact. There is no way to keep track of time, he says, without anything capable of marking regular intervals. Whether an attosecond passes or a femtosecond passes makes no difference to the particles in that soup. And notice that this is not the claim that the difference is too small to measure. It is the claim that there is nothing in the universe that constitutes the difference. Now comes the move that makes the argument extraordinary. Penrose points out that this description does not only fit the distant past, it fits the distant future just as well. Wait long enough, and every star fades. Wait longer, and what is left is black holes and free particles. Wait very much longer, and even the black holes decay. And what remains, at the end of that, is overwhelmingly massless. Photons, gravitons, radiation drifting through an emptiness that has no features. Nothing left has a rest mass, which means nothing left has a scale, which means once again a clock cannot be built. And in the alternative endings, a big crunch or a big rip, clocks fare no better. There is nothing stable to build one out of in a universe being torn apart either. You could still argue that duration exists conceptually even if nothing whatsoever can measure it. And researchers genuinely disagree about whether that is a coherent position. Henrik Zinkernagel, at the University of Granada in Spain, who has worked on exactly this disappearance of time from cosmology, states the hard version as plainly as it can be stated. If time is what is measured on a clock, and there are no clocks, then there is no time. Whether or not you accept that, the inability to build a clock is at minimum evidence that time has lost one of its defining features, and here is where it turns into something else entirely. If both ends of cosmic history are scale-free, if neither the beginning nor the far future contains anything that could distinguish an enormous duration from a tiny one, then in a very precise mathematical sense, the two are not distinguishable from one another. Penrose noticed this and said so directly. The Big Bang closely resembles the remote future, not poetically, geometrically. and he proposed that they might not merely resemble each other, but might actually be successive stages of one continuous history, that when time reaches its end, having lost every property that would let it be measured, it can be rescaled and continued, and what continues is a new beginning. He calls the cycles aeons. The theory is called conformal cyclic cosmology. I want to let that land properly. Roger Penrose spent his career establishing that time comes to an end. He proved the wall exists, and then, following the same argument all the way to the far side, he found a reason why the wall might be a door, and the man most responsible for the idea that time is finite proposed the mechanism by which it might not be. The supposed slayer of time became its saviour. The logic underneath it is precise rather than mystical, which is worth saying because the idea attracts a certain amount of nonsense. If everything remaining is massless, no physical process can define a scale of distance or time. The geometry keeps its angles and loses its sizes, a property called conformal invariance, which massless particles have and massive ones do not. And a geometry that has lost track of size can be mathematically rescaled without changing any of the physics inside it. So the infinitely dilute, infinitely spread out far future of one aeon can be rescaled to match the dense, smooth beginning of the next. It is not that the universe shrinks, it is that the word shrink stops applying. Now the honesty, because this theory has real weaknesses and Penrose is the first to say so. Not everything in the far future will be massless. Electrons very probably survive. Nothing is known that would remove them. And if electrons survive, then a clock can in principle be built, and the whole argument fails. Penrose has suggested that electrons might somehow lose their mass over spans of time, long enough for the question to matter, and he freely admits that this is speculative and uncertain. He has called it one of the more problematic aspects of the theory, in those words, in public. That is not a critic's characterization. That is the author's. There is a second objection at the other end. If the early universe genuinely had no sense of scale, how did it manage to expand and thin out and cool down? Those are all changes in scale. Something must have been keeping score, and there have been claimed observational signatures. Penrose and a collaborator reported in 2010 that they had found concentric rings of unusually low temperature variation in the oldest light in the sky, which they interpreted as the imprint of black holes colliding in a previous aeon. Later work reported small anomalous spots, called Hawking points, interpreted as the final evaporation of supermassive black holes from a previous cycle. Independent groups reanalyzed the same data and found the features entirely consistent with what ordinary noise already produces. Neither claim is accepted. What I will say in the theory's favour is that it made a testable prediction at all, which is more than most cyclic cosmologies manage, and that the tests have come back inconclusive rather than damning. So this is the second loss. The arrow went first, duration went second, and notice that the Twilight picture has now done something the two camps could not do. It has produced a specific, worked, physically motivated account of a universe in which time has partly ended and partly has not, which is precisely the kind of answer that a yes or no question cannot generate. But even with the arrow gone and duration gone, something is still left, and it is the last thing, and it is the strangest, and it is where the whole evening has been going. Part 13. What melts last? What survives, after the arrow and after duration, is order, the sequence of cause and effect, and this is what makes time different in kind from space, so it is worth being careful about it. Space allows arbitrary arrangements. A keyboard and a sticky note can sit in any relative position, left, right, above, behind, and there is no sense in which one of them has to be there because of the other. Their spatial relationship carries no obligation. Time does not work like that. Typing on a keyboard and letters appearing on a screen are not merely adjacent in a sequence. The first produces the second. Order in time is not a description of layout, it is a description of dependence. So even in a universe with no direction and no duration, you would still have that. Things would still happen because of other things. Under certain conditions, that goes too. The idea traces back to the 1980s, when Stephen Hawking and James Hartley proposed that the Big Bang was not a beginning, but the moment at which time and space differentiated from each other. Work the mathematics in what is called imaginary time, and the initial singularity simply disappears. What is left is a smooth closed surface with no edge, and nothing to point at as a start, a shape rather than an origin. Hawking's own formulation of it is one of the best sentences in 20th century physics. The boundary condition of the universe is that it has no boundary. Near the beginning, on this picture, what we call time rotates into being a fourth dimension of space, and the question of what came before stops having a target, in the same way that the question of what lies north of the North Pole stops having a target. String theory suggested a way the same thing could happen at the other end. If our universe is a membrane floating in a higher dimensional space, and that is a real proposal, not a metaphor, then picture a leaf blowing in the wind, with us trapped on the surface of it like caterpillars. Ordinarily we crawl about freely in our four-dimensional prison. But if the leaf is buffeted about violently enough, we become pinned. To make any progress along the membrane, we would need to travel faster than light, and that is not available. So every process stops, because every process requires some form of motion, and motion is what has become unavailable. Viewed from outside the timelines of our lives, those threads of successive moments do not come to an end. They curve. They become lines through space. The membrane is still four-dimensional. It is simply that all four of those dimensions are now spatial ones. What was a sequence of moments has become a shape, and the most unsettling feature of that scenario is that nobody living through it would notice. All clocks slow together, so there is no reference against which to detect the slowing. Nothing would feel like anything. What you would observe instead is distant galaxies appearing to accelerate away from you, which is, of course, exactly what astronomers do observe, and which is currently attributed to dark energy. Some people have wondered aloud whether the acceleration we measure might be the observable face of time converting itself into space. I want to be very clear that this is speculation, and that it is not the mainstream reading of the data. Dark energy makes up about 68% of the energy content of the universe on the standard account. The acceleration was established by two independent supernova teams in 1998, and it earned a Nobel Prize in 2011. Nothing about that has been overturned. The Brainworld reading is a minority thought hanging off the edge of a well-supported result, and you should file it accordingly. Now, the last piece. Even without duration and without causal order, you could still in principle assign events to points and lay them out on a timeline. Position, the bare fact of when. String theorists have gone after that too at black hole singularities, using an idea called the holographic principle. A hologram is a flat object that creates the illusion of depth. It looks as though a solid thing is suspended in three-dimensional space, and it is not. The whole appearance is encoded on a surface. The holographic principle proposes that our entire universe works the same way, that a complicated system of interacting quantum particles, with no depth of its own, generates the appearance of an extra-spatial dimension. The idea came out of black hole thermodynamics, when it was noticed in the 1970s that the entropy of a black hole scales with the area of its horizon rather than with its volume, which is not how information is supposed to work. Gerard 't Hooft proposed the principle in 1993, Leonard Susskind developed it in 1994, and in 1997, Juan Maldacena made it concrete with a specific correspondence between a gravitational theory in a curved five-dimensional space and an ordinary quantum theory living on its four-dimensional boundary. It has become the most cited paper in modern theoretical physics. But not every image can be a hologram. The encoding requires very specific patterning, and if a hologram is scratched or damaged, the illusion is ruined. In the same way, not every particle system generates a universe like ours. The system needs precise regularities. When a system that lacks them develops them, a spatial dimension emerges, and when a system loses its orderliness, the dimension goes away. Now watch a star collapse. To us it is a three-dimensional object. In the holographic description it corresponds to a pattern in some two-dimensional particle system. As the gravity increases, the corresponding flat system vibrates more and more violently. And when a singularity forms, the order breaks down entirely. The way an ice cube melts, the neat lattice of water molecules dissolving into the disarray of a liquid. The third dimension does not get crushed. It dissolves, and time follows it out. Remember that inside a black hole your position in time is determined by your distance from the center. That distance lives in the spatial dimension that is now disintegrating. So as the dimension goes, your watch begins to spin uncontrollably. Picture it, because this is the actual texture of the thing we have spent the evening approaching. You are inside, you look at your wrist, the hands are moving, and you can see them moving, and then the question of what they are moving through stops having an answer. You look at your hand, and the distance between your hand and your eye is not larger or smaller. It is not a distance. You try to ask where something is, and the question comes back malformed, like asking what colour a number is. There is no flash, there is no wall, there is no impact, and nothing hits you. There is only a quiet, orderly failure of the questions, one after another, each one dissolving before it can be finished, while the world itself carries on doing whatever it is doing without any of them. The consequences are strange and specific. Attempts to measure the positions of objects find them seemingly occupying several places at once. Spatial distances lose their meaning, so objects can apparently move from one place to another without traversing what lies between, and that provides a route by which the imprint of anything that crossed the horizon could get back out, because the horizon itself is defined geometrically, and if the geometry has dissolved, the horizon loses its clear definition too. That is Thomas Hertog and Gary Horowitz's territory, from a paper in 2005 later extended with Netta Engelhardt. A crunch singularity in the gravitational description corresponding to something perfectly well behaved on the other side of the correspondence. Though the honest caveat is that these results are obtained in a universe with a negative cosmological constant, and ours appears to have a positive one. It is a laboratory, not a map. And here is the crucial insight, the one that undoes the comfortable answer we were given halfway through the evening. String theory does not do what everybody expected quantum gravity to do. It does not politely smooth the singularity into a small dense lump and leave the rest of the universe untouched. It says the breakdown of space and time is broader than the singularity, and that its effects extend well beyond it. The problem was never localized. We simply drew the boundary in the wrong place, and even this does not finish the job. The holographic description still relies on a notion of time within the particle system doing the encoding. Time has been moved, not eliminated. There are physicists working right now on constructing a notion of dynamics that does not presuppose time at all, and until somebody succeeds, time stubbornly persists, not because it has been proven fundamental, but because it is so deeply woven into the structure of physics that nobody has yet managed to imagine its complete absence. So, Wheeler's sentence: Einstein's equation says this is the end, and physics says there is no end. We can finally say what is wrong with it, and the answer is nothing. Both halves are true simultaneously, and they always were. The equations really do terminate, and physics really does continue. What ends is not the universe and not the equations. What ends is the applicability of the word. There is no last moment, and there is no next moment either, because both of those phrases require a structure that is no longer present to hold them up. It was never a contradiction. It was two accurate descriptions of a situation for which we do not have vocabulary, which means the two escape routes we spent the middle of tonight examining were never repairs. They were trades. Take the branch where time truly ends, and you surrender the assumption that the laws of physics are laws about change, which is the founding assumption of the subject. Take the branch where time never ends, and you surrender the finiteness of the past, and you inherit an entropy bill that nobody has been able to pay in 130 years. And take the Twilight picture, which I think is the most honest of the three, and you surrender something more intimate, the idea that time is one thing at all. And now the quiet part, which is the reason this subject sits differently from every other apocalypse. Look at what time actually loses in order, and look at what each of those things is for. We rely on directionality for development and for evolution. No arrow, no growth, no memory, no learning. We rely on duration and scale for building complex structures. No ruler, no chemistry, no cells. We rely on causal ordering for any process to unfold at all. No dependence, no action, no consequence. We rely on spatial separation to create pockets of order inside a universe that is running down. No separation, no shelter, nothing that can hold itself apart from the general dissolution long enough to be anything. Every single property that time sheds on its way out is a property that living things require in order to exist, which means the end of time is the one event in the entire history of the universe that has no witness, not because everyone happens to have died first, because the conditions for there being an observer and the conditions for there being an end are mutually exclusive. We can describe it, we can argue about it. Nobody will ever be present for it, in the same way that no one is ever conscious at the exact moment of their own death. I said at the beginning that the end of time would be the end of all endings, and I meant it as a technical statement about transitions. It has a smaller meaning now, at the far side of the evening. There will be no one there to call it an ending. There will not even be the machinery for the word. And I want to leave you with the bullseye, because it has been sitting under everything tonight. Every infinity we have looked at turned out, on closer inspection, to be a finite structure that we did not have the resolution to see. The infinitely bright point was a disk with rings around it. The infinitely dense point may be a small bundle boiling away at the heart of a black hole. Physics has a long, encouraging history of walking up to its own infinities and finding furniture behind them. So which is this? Is the end of time one more bullseye, a smoke alarm from a theory standing outside its own doorway? Or is it the one case in the history of the subject where the point is real? Nobody knows. That is the honest answer, and it is not a small one. 60 years after Penrose, with the best confirmed theory in science on one side and 23 centuries of logic on the other, this paradox of time is still sitting there, unmoved, disturbing enough that the people who work on it tend not to raise it at dinner. And here is the last thing, which I think is the strangest of all. Every attempt anyone has made to describe the end of time, every equation, every proposal, every one of the ideas we've gone through tonight, has had to use time in order to do the describing. The bounce happens, the dimension dissolves, the aeon gives way to the next, happens, dissolves, gives way. We cannot even talk about it without borrowing the thing we're trying to lose,